Greetings everyone, and welcome to this class walkthrough. In this video, we'll explore the complete design and implementation of a professional grade class, the BankAccount class. We'll examine how it's structured across a header file, an implementation file, and a main program, and we'll talk about how these pieces work together to produce clean, maintainable, and reusable code. Our use case is a small-scale banking application. Imagine you're building a program for a local credit union or a personal finance tracker. It needs to manage account holders, track balances, prevent invalid transactions, and produce clear account statements. The BankAccount class is our solution. It encapsulates data and behaviors for a single account, letting us create accounts, deposit and withdraw funds, transfer money, and print details in a neat, user-friendly format. This mirrors exactly what you'd see in the core of a real-world financial system. Let's first take a look at our header file for our BankAccount class. In the header file is where we declare the interface of our class, what the class looks like to the rest of the program. At the top, we have a professional file comment, something that's essential in collaborative environments to communicate author, date, and purpose. This is followed by an include guard, which prevents multiple inclusions of the same file during compilation. Without it, we could get redefinition errors. We include the string library because we need to store the account owner's name, and the IOStream library for output operations. The using namespace STD is here because in our course we use it for simplicity, though in professional, large-scale environments you might avoid it in headers to reduce the risk of naming conflicts. For the purpose of this class, we will always include it to keep things simple. Inside the class definition, our private data members, string owner and double balance, represent the state of a bank account. They're private to protect them from direct modification by outside code, which is a core concept in encapsulation. We also have a private helper function, enforce invariant, which enforces a class invariant, a condition that should always be true for any valid object. In this case, the invariant is that the account balance must never be negative. In the public section, we have constructors, which are special functions that run automatically when an object is created. The default constructor sets a safe initial state, an owner of unknown, and a zero balance. The parameterized constructor lets us create an account with specific starting values. We have getters, getOwner and getBalance, that provide read-only access to our data members, and a setter. setOwner that allows changing the owner, but only after validating that the name isn't empty. Then we have our core behaviors, deposit, withdraw, and transfer to, that perform real banking operations while enforcing rules such as no negative amounts and no overdrafts. These methods return meaningful results or throw exceptions to indicate problems. Finally, we declare a friend function for the stream insertion operator, which allows us to send a bank account object directly to cout or another output stream. This makes displaying account details clean and intuitive. This is an example of operator overloading, a feature that lets objects behave more like built-in types. Next, we will look at the implementation file for our bank account class. We include the header file so the compiler knows the class's interface, and we also include libraries for exceptions, assertions, and for output formatting. The enforce invariant method is implemented first. This uses an assert to check that the balance is always non-negative. This is a defensive programming technique. It's like adding a safety net to catch logic errors during development. If this condition fails in a debug build, the program will stop immediately, pointing us to the problem before it can cause bigger issues. Our default constructor uses a member initializer list to set owner and balance, then enforces the invariant. The parameterized constructor also uses an initializer list, but first checks that the initial balance isn't negative. This is an example of input validation. The getters simply return their values. The setter validates the input string before assignment, ensuring we don't have accounts with blank owner names. The deposit function enforces a rule that deposits can't be negative, then updates the balance and rechecks the invariant. The withdraw function ensures the amount is valid, checks for sufficient funds, and either processes the withdrawal or returns false. The transfer to function prevents self-transfers and negative amounts and then performs a withdrawal from one account followed by a deposit into the other. This shows code reuse. We use existing methods, withdraw and deposit rather than rewriting the logic. Finally, the overloaded stream insertion operator formats the output neatly. It uses fixed and set precision too, from IOmanip to display the balance like money. This is an example of stream manipulation in C++. And finally, we move to our main program. In our main function, we're creating a driver program, a simple, focused application that demonstrates the class's capabilities. We start with a printed welcome banner so the user knows what's being demonstrated. We create two bank account objects, account 1 for Kevin with $500 and account 2 for Sam with $200. Printing them shows our overloaded stream insertion operator in action. Account owner, Kevin, balance $500, account owner, Sam, balance $200. Next, Kevin deposits $150. Deposits are validated in the deposit method, then the balance updates to $650. Printing confirms the change. Account owner, Kevin, balance $650. Sam withdraws $50. The withdrawal method validates the amount and checks funds, then deducts the amount, leaving $150. Now we see that the account owner, Sam, has a balance of $150. Kevin transfers $200 to Sam. The transfer method calls withdraw and deposit under the hood, so both validation and invariant checks happen automatically. Afterward, Kevin has $450 and Sam has $350. Lastly, Sam tries to withdraw $1,000. Since his balance is only $350, the withdrawal method refuses and returns false, so the program prints a failure message and his balance remains unchanged, showing account owner, Sam, balance $350. The program ends with a closing demo complete message, marking the end of our demonstration. Let's wrap up the concepts we demonstrated. This bank account example ties together multiple core C++ concepts. Encapsulation, keeping data private and exposing controlled access. Constructors, automatically setting up an object in a valid state. Validation, preventing bad data from entering the object. Defensive programming, using invariants and assertions to catch errors early. Code reuse, calling existing methods within other methods to avoid repetition. Operator overloading, making objects interact naturally with the language's syntax. Separation of interface and implementation, organizing code into headers and implementation files for maintainability. Thanks for following along. We will see you in the next video.